Right now, 8 light minutes away from where you were lying, a nuclear reactor the size of 1.3 million Earths is fusing approximately 620 million metric tons of hydrogen into helium every single second. It has been doing this for 4.6 billion years, without stopping, without slowing, without maintenance, without any instruction from anyone. It requires no fuel deliveries. It produces no waste that does not eventually become the next generation of stars. It has provided the energy for every sunrise you have ever seen, for every plant that has ever lived, for every ocean current, for every wind, for every calorie of food you have ever eaten, for the entirety of human civilization and all the civilizations that preceded it. And it has done all of this while consuming less than half of its original fuel supply. That reactor is the sun, and it is, by virtually every measure astronomers use, an utterly ordinary star. Not the largest, not the brightest, not the hottest, not the most massive, not the most energetic, not the longest lived. In the Milky Way, a galaxy of somewhere between 100 and 400 billion stars, the sun is a perfectly average, middle-aged, mid-sized, middle luminosity star that will live and die without drawing any particular attention from the broader cosmos. The fact that this perfectly ordinary star is the most important object in the observable universe from the perspective of every living thing on Earth is itself one of the most beautiful facts in all of science. Stars are extraordinary, every one of them, and the story of stars is the story of the universe itself, because stars are how the universe makes everything that is not hydrogen and helium, which means stars are how the universe eventually made us. Tonight we rest in stars. Not metaphorically, but literally, the iron in your blood was made in a star. The carbon in every molecule of your DNA was forged in the heart of a dying star. The oxygen you are breathing was produced partly in stellar cores and partly by billions of years of photosynthesis powered by a star. You are made of stars, and tonight you are resting in the light of one. Every fact I am going to share with you is true. Every number is the best estimate of the best scientists who have ever studied these questions. Stars are more diverse, more violent, more patient, more beautiful, and more intimately connected to your existence than most people ever fully appreciate. And tonight, they are your bedtime story. Take a slow, deep breath in, all the way gently until your lungs are comfortably full. Hold it for just a moment and breathe out slowly, completely, letting your body soften, let your weight settle, let your hands be open. Somewhere above you, past the ceiling and the clouds and the atmosphere and the orbiting satellites and the moon, the sun is burning even on the night side of the earth, even now, and beyond the sun, in every direction, across unimaginable distances. Stars are burning too. Tonight they are all burning for you. A star is, at its core, a battle between gravity and pressure. Gravity is the force that pulls every part of a massive object toward every other part, trying to collapse it into a single dense point. Pressure is the force that pushes outward against this collapse, provided by the thermal energy of the hot gas in the star's interior. A star exists in a state of balance between these two forces called hydrostatic equilibrium. Every point in the star's interior is exactly where it needs to be, the pressure from below exactly balancing the weight of everything above. This balance is maintained by the nuclear reactions in the core that continuously produce the heat needed to maintain the pressure. This balance is also self-regulating in a beautiful way. If the star's core were to cool slightly, the pressure would drop, gravity would win temporarily, and the core would contract and heat up, restoring the pressure. If the core were to heat up too much, the increased pressure would push the star outward, expanding it and cooling it until equilibrium was restored. Stars are thermostats. They run at the temperature required to balance their gravity, and they maintain that temperature automatically through feedback loops built into the laws of physics. The nuclear fusion that powers stars, at least stars like the Sun, proceeds through what is called the proton-proton chain. In this process, 4 protons, the nuclei of hydrogen atoms, are converted into one helium-4 nucleus, which consists of 2 protons and 2 neutrons. In the process, 2 of the original protons become neutrons by releasing a positron and a neutrino, and 2 gamma-ray photons are produced. The helium-4 nucleus has slightly less mass than the 4 original protons, and this mass difference, in accordance with Einstein's equation E equals mc squared, is converted entirely into energy. The mass difference per fusion event is very small, about 0.7% of the original hydrogen mass, but the Sun fuses 620 million metric tons of hydrogen per second, converting about 4.3 million metric tons of that mass directly into energy every second. The energy released is carried outward from the core by photons, but the interior of the Sun is so dense that these photons do not travel in straight lines. They are continuously absorbed and re-emitted by the plasma, performing what physicists call a random walk. The average distance a photon can travel before being absorbed and re-emitted is tiny, much less than a centimeter. Estimates suggest it takes a photon between 10,000 and 170,000 years to random walk its way from the center of the Sun to the surface, at which point it escapes into space and travels to Earth in only 8 minutes and 20 seconds. The photons of sunlight reaching your face on a sunny afternoon may have been produced in the solar core during the last ice age, or during the time of the ancient Egyptians, or during the earliest period of human civilization. They spent most of their existence trapped in the dense plasma of the Sun's interior, bouncing randomly, before finally escaping and making the brief journey to your eyes. Stars are classified by their surface temperature and luminosity on a diagram called the Hertzsprung-Russell diagram, or HR diagram, named after the Danish astronomer Egnar Hertzsprung and the American astronomer Henry Norris Russell, who independently developed it in the early 20th century. On the HR diagram, stars are plotted with temperature on the horizontal axis, decreasing from left to right, and luminosity on the vertical axis, increasing from bottom to top. Most stars fall along a diagonal band running from hot and bright in the upper left to cool and dim in the lower right, called the main sequence. Stars on the main sequence are in the stable hydrogen-burning phase of their lives. A star's position on the main sequence is determined almost entirely by its mass. More massive stars burn hotter and brighter and sit toward the upper left, while less massive stars burn cooler and dimmer and sit toward the lower right. The spectral classification of stars follows a sequence originally organized by temperature, from hottest to coolest, using the letters O, B, A, F, G, K, and M. Astronomers have traditionally remembered this sequence with the mnemonic "Oh Be a Fine Girl, Kiss Me," though more recently, the sequence has been extended with the addition of cooler classes L, T, and Y for objects at the boundary between stars and brown dwarfs. The Sun is classified as a G-type main sequence star, or a G-dwarf, with a surface temperature of about 5,778 Kelvin. O-type stars are the hottest and most luminous main sequence stars, with surface temperatures above 30,000 Kelvin. They appear blue-white and are extraordinarily rare. The entire Milky Way contains perhaps only a few hundred O-type stars. They are the most massive of all main sequence stars, with masses typically between 15 and 90 solar masses, and they are profligate with their fuel, burning through their hydrogen supply in only a few million years. An O-type star lives and dies before the orbit of a planet like Earth can complete even 0.01% of its journey around the galactic center. Their deaths are correspondingly violent. The most massive O-type stars die in supernova explosions of extraordinary power, or in even more energetic events called hypernovae. B-type stars have surface temperatures between about 10,000 and 30,000 Kelvin and are also blue-white, though somewhat less extreme than O-type stars. Rigel, the bright blue-white star at the foot of Orion, is a B-type supergiant. It is located about 860 light-years from Earth and has a luminosity of about 120,000 times that of the Sun. If Rigel were placed where the Sun is, it would be blindingly bright, visible in daytime, and its radiation would have stripped away Earth's atmosphere and sterilized its surface long ago. A-type stars have surface temperatures between about 7,500 and 10,000 Kelvin and appear white to slightly blue. Sirius, the brightest star in the night sky as seen from Earth, is an A-type main sequence star. Vega, one of the brightest stars visible from the northern hemisphere and one of the vertices of the Summer Triangle, is also an A-type star. A-type stars live for about 1 to 3 billion years, shorter than the Sun's 10 billion year lifetime, but long enough to potentially host planetary systems of substantial age. F-type stars are hotter than the Sun, with surface temperatures between about 6,000 and 7,500 Kelvin. The North Star, Polaris, is classified as an F-type supergiant, though its classification is complicated by the fact that it is a pulsating variable star in a multiple star system, as we will discuss shortly. Procyon, one of the nearest bright stars to the Sun at only 11.4 light-years, is an F-type subgiant. G-type stars, the class of the Sun, have surface temperatures between about 5,200 and 6,000 Kelvin. They appear yellow-white. Alpha Centauri A, the largest star in the nearest star system to the Sun, is a G-type star very similar to the Sun, with about 1.1 solar masses and 1.5 solar luminosities. G-type stars have main sequence lifetimes of about 10 billion years, long enough for complex life to evolve on suitable planets if life has the opportunity to begin. K-type stars are cooler than the Sun, with surface temperatures between about 3,700 and 5,200 Kelvin. They appear orange. Epsilon Eridani, one of the nearest Sun-like stars to the solar system at 10.5 light-years, is a K-type star. K-type stars have main sequence lifetimes of 15 to 30 billion years, significantly longer than the current age of the universe. Some researchers have argued that K-type stars may be among the most promising hosts for life-bearing planets, because their longer lifetimes give more time for evolution, while their greater activity levels, compared to the coolest stars, may be balanced by the stability of their radiative output compared to the most energetic stars. M-type stars, also called red dwarfs, are the coolest and least luminous of the main sequence stars. With surface temperatures below about 3700 Kelvin, they appear red or deep orange. Red dwarfs are by far the most common type of star in the universe. About 75 to 80% of all stars in the Milky Way are M-type. The nearest star to the Sun, Proxima Centauri, is a red dwarf. Barnard's star, the second nearest star system, is a red dwarf. The TRAPPIST-1 system, with its 7 planets including several in the habitable zone, orbits a red dwarf 40 light-years away. Red dwarfs are extraordinarily long-lived. The least massive red dwarfs, with masses just above the threshold for hydrogen fusion, about 8% of the Sun's mass, have estimated main sequence lifetimes exceeding 10 trillion years, nearly 1,000 times the current age of the universe. Not a single red dwarf has ever died in the history of the universe, because none has yet run out of fuel. In the far future, when the Sun and all other stars of comparable or greater mass have long since died, red dwarfs will still be burning, the last stellar fires in a cooling universe. Let your breathing be slow and easy. The red dwarfs are the most patient things in the universe. They have been burning since shortly after the Big Bang and will continue burning long after every other type of star has gone cold. Tonight, somewhere in the dark, red dwarfs are glowing with a dim, patient red light. Their surfaces barely hotter than some industrial furnaces on Earth, their hearts quietly converting hydrogen to helium at a rate that will sustain them for geological ages beyond anything we can meaningfully imagine. Beyond the main sequence on the HR diagram lie the giants and supergiants. When a star exhausts the hydrogen in its core, the core contracts and heats up while the outer layers of the star expand dramatically. The star becomes a red giant, or for more massive stars, a red supergiant. These stars have surface temperatures much lower than their main sequence counterparts. Because the energy from the contracting core and the new hydrogen-burning shell is spread over a much larger surface area. But because their surface area is so enormous, their total luminosity can be very high. Betelgeuse, the bright red-orange star at the shoulder of Orion, is a red supergiant and one of the largest stars visible to the naked eye. Its diameter is estimated at roughly 700 to 1,000 times that of the Sun, though these measurements are difficult because the star's outer atmosphere is diffuse and variable. If Betelgeuse were placed at the center of our solar system, its surface would extend roughly to the orbit of Jupiter. The star is also variable in brightness, pulsating irregularly over timescales of months to years due to complex convective processes in its enormous outer envelope. In late 2019 and early 2020, Betelgeuse dimmed significantly, triggering widespread speculation that it might be about to go supernova. This event, nicknamed the Great Dimming, was later attributed to a combination of a cool patch on the star's surface and a dust cloud ejected during a surface mass ejection event. Antares, the brightest star in the constellation Scorpius, is another prominent red supergiant, with a diameter estimated at about 700 solar diameters. Its name, which means rival of Mars in Greek, reflects its distinctive reddish color, comparable in appearance to the planet Mars. Like Betelgeuse, Antares is variable in brightness and is expected to end its life in a supernova explosion within the next few 100,000 years. When Betelgeuse or Antares explodes, it will be visible from Earth in daylight, as bright as the full moon, for days to weeks. The largest stars known to science are the hypergiants, stars of extraordinary size that strain at the upper limits of stellar physics. UY Scuti, a red hypergiant in the constellation Scutum, has a radius estimated at about 1,700 solar radii. If it were placed at the center of our solar system, its surface would extend beyond the orbit of Saturn. Canis Majoris, another red hypergiant, has been estimated at up to 2,000 solar radii, though recent measurements suggest a more conservative estimate. Stephenson 218, a recently studied red supergiant in the star cluster Stephenson 2, has been estimated at about 2,150 solar radii, making it possibly the largest known star by volume. These hypergiant stars are so large and luminous that they are barely stable. Their surface gravity is low enough that their outer layers are continuously escaping into space in powerful stellar winds, ejecting mass at rates millions of times higher than the solar wind. They are ephemeral objects on a stellar scale, expected to persist in their current form for only a few thousand years before the mass loss or an internal instability triggers their explosive end. Variable stars, stars whose brightness changes over time, come in many distinct types and have been extraordinarily important in the history of astronomy. Delta Cepheid, the prototype of the Cepheid variable class, is a pulsating star that expands and contracts over a period of about 5.4 days, brightening as it contracts and dimming as it expands, due to a self-sustaining cycle of opacity changes in its outer layers. The period of a Cepheid variable star's pulsation is tightly correlated with its intrinsic luminosity. Through a relationship discovered by Henrietta Leavitt working at the Harvard Observatory in 1908 and published in 1912. Leavitt was studying variable stars in the small Magellanic Cloud and noticed that the Cepheids with longer pulsation periods were systematically more luminous than those with shorter periods. Since all the stars in the Magellanic Cloud are at roughly the same distance from Earth, differences in apparent brightness directly reflected differences in intrinsic luminosity. The period-luminosity relationship she discovered became one of the most important tools in astronomy. By measuring the pulsation period of a Cepheid variable anywhere in the universe, astronomers can determine its intrinsic luminosity, and by comparing that to its apparent brightness, they can calculate its distance. Edwin Hubble used Cepheids to measure the distance to the Andromeda Galaxy in 1924, confirming that it was far outside the Milky Way. Type 1a supernovae, which were used to discover the accelerating expansion of the universe, were calibrated using Cepheid distances. The period-luminosity relationship, discovered by a woman working as a human computer at Harvard, denied a PhD because of her gender, is woven into the foundation of modern cosmology. Lyra variables are another important class of pulsating stars, related to Cepheids but typically found in old stellar populations like globular clusters. Mira variables are cool red giant stars that pulsate over periods of months to years with dramatic brightness changes. Mira itself in the constellation Cetus, varies from bright enough to be seen easily with the naked eye to too faint to see with the naked eye without a telescope over a period of about 330 days. Long period variables like Mira are stars in late stages of their evolution, pulsating as they shed their outer envelopes in slow, massive stellar winds. Let your breathing be slow and steady, in and out. The Cepheid variables are pulsating in galaxies across the universe tonight. Their rhythmic brightness changes encoding information about their distance, like cosmic lighthouses flashing their location across billions of light years. Henrietta Leavitt decoded that message, and the universe has not looked the same since. Most stars do not live alone. The majority of sun-like and more massive stars exist in binary or multiple star systems, where two or more stars orbit their common center of mass. Our nearest neighbor, the Alpha Centauri system, is a triple star system. Alpha Centauri A and B orbit each other over a period of about 80 years, while Proxima Centauri orbits much farther out with a period of about 550,000 years. Sirius, the brightest star in the night sky, is a binary system consisting of Sirius A, a bright A-type main sequence star, and Sirius B, a white dwarf. Polaris, the North Star, is a triple star system. Polaris AB is a close companion orbiting Polaris A over a period of 30 years, and Polaris B orbits the pair at a much greater distance. The existence of binary stars has profound consequences for stellar evolution. When two stars orbit each other in a close binary system, they can exchange mass as they evolve, with one star accreting material from the other. This mass transfer can dramatically alter the evolutionary histories of both stars. A white dwarf in a close binary system can accrete material from a companion star until it approaches the Chandrasekhar limit of 1.4 solar masses, at which point it undergoes a thermonuclear explosion, a Type 1 supernova. Neutron stars in close binary systems can be spun up by infalling material from a companion, becoming millisecond pulsars. The merger of two neutron stars in a tight binary creates the conditions for the production of heavy elements like gold, platinum, and uranium through a process called the R process of nucleosynthesis. The gold in any ring on your finger was made in a neutron-star merger, a cataclysmic collision between two of the densest objects in the universe. Contact binaries are particularly dramatic examples of the interaction between stars in close pairs. In a contact binary, the two stars are so close to each other that their outer atmospheres actually touch and merge, forming a common envelope of gas surrounding both stellar cores. The two cores orbit each other within this shared envelope, separated by less than the diameter of either star. W Ursae Majoris, visible to the naked eye in Ursa Major, is a well-studied contact binary with a period of only about 8 hours. Contact binaries are expected to eventually merge into a single, rapidly rotating star. The formation of a star begins in a molecular cloud, a cold, dense region of the interstellar medium where hydrogen exists primarily in molecular form rather than atomic form, and temperatures can be as low as 10 Kelvin, only 10 degrees above absolute zero. Molecular clouds can span dozens or hundreds of light years and contain enough mass to form thousands or millions of stars. The Orion Molecular Cloud The nearest large molecular cloud to the solar system is about 1,500 light-years away and spans hundreds of light-years, containing enough material to form thousands of sun-like stars. The collapse of a molecular cloud to form stars begins when the cloud is compressed by a disturbance, perhaps a shock wave from a nearby supernova or the passage of the cloud through a galactic spiral arm. If a region of the cloud becomes dense enough, gravity overcomes the thermal pressure and magnetic fields that support the cloud, and that region begins to collapse. As it collapses, it heats up through the conversion of gravitational potential energy into thermal energy and begins to spin faster as it conserves angular momentum. The spinning collapse flattens into a disk with the central concentration of mass growing into a protostar and the surrounding disk becoming the protoplanetary disk from which planets eventually form. A protostar is not yet a true star. It is accreting material from the surrounding disk and collapsing, heating up as it does so, but it has not yet become hot enough in its core for nuclear fusion to ignite. As the protostar's core temperature rises, it first undergoes deuterium burning when the core temperature reaches about 1 million Kelvin, a temporary energy source that slows the collapse. True hydrogen fusion ignites when the core temperature reaches about 10 million Kelvin, at which point the protostar has become a zero-age main sequence star, or ZAMS, and the era of stable stellar burning has begun. Young stars are often surrounded by their birth material, wrapped in cocoons of gas and dust that absorb the star's light and re-emit it as infrared radiation. They are also often violently active, with intense magnetic activity driving powerful jets of material from the star's poles, bipolar outflows that can extend for many light years and are among the most dramatic structures in the interstellar medium. The Herbig-Haro objects, beautiful structures of glowing gas that can be seen in images of stellar nurseries, are formed when these jets slam into the surrounding interstellar medium. The molecular cloud from which the solar system formed contained many different types of atoms and molecules, including all the heavy elements that had been synthesized by previous generations of stars and distributed through the interstellar medium by stellar winds and supernova explosions. The protoplanetary disk that surrounded the young sun was therefore chemically rich from the beginning, containing not just hydrogen and helium, but carbon, oxygen, nitrogen, silicon, iron, and all the other elements of the periodic table. The planets, moons, asteroids, comets, and ultimately the living organisms of Earth are all made from this inherited chemical richness. The concept of stellar populations reflects the chemical evolution of galaxies over cosmic time. Population 3 stars are the hypothetical first generation of stars in the universe, formed from the primordial gas of the Big Bang, which contained only hydrogen, helium, and trace amounts of lithium. Population 3 stars had no heavy elements and are thought to have been much more massive than most stars today, because the absence of heavy elements meant the cooling mechanisms that prevent modern molecular clouds from collapsing into very massive stars were unavailable. Population 3 stars lived briefly, died violently in supernovae, and seeded the interstellar medium with the first heavy elements. Population 2 stars formed from the metal-poor gas enriched by the first supernovae. They are old stars, typically more than 10 billion years old, found in globular clusters in the halos of galaxies. The oldest known star, HD 140283, nicknamed the Methuselah star, is a population 2 star about 190 light-years from Earth, with an estimated age of about 13.7 billion years, nearly as old as the universe itself. Its composition, extremely low in elements heavier than helium, reflects the limited nucleosynthesis that had occurred in the universe by the time it formed. Population 1 stars are the youngest and most metal-rich stars, formed from gas that has been enriched by many generations of stellar nucleosynthesis. The Sun is a population 1 star, containing about 2% heavy elements by mass. Population 1 stars tend to be found in the spiral arms of galaxies, where ongoing star formation is concentrated, and include all the main sequence stars of type O through F that are currently forming in stellar nurseries. The process by which stars create heavy elements and distribute them through the interstellar medium is called stellar nucleosynthesis, and it was worked out in detail by Fred Hoyle, William Fowler, and Margaret and Jeffrey Burbidge in a landmark 1957 paper known as B to FH. The paper showed how virtually all of the elements of the periodic table, from carbon to iron, could be synthesized in stellar interiors through various nuclear reactions. Iron 56 is the most tightly bound of all atomic nuclei, meaning it cannot release energy by either fission or fusion. When a massive star's core is converted to iron, the energy generation stops, gravity wins, and the core collapses in milliseconds. The resulting supernova distributes all the elements synthesized in the star's lifetime into the interstellar medium, where they become available as building material for the next generation of stars and planets. Elements heavier than iron cannot be produced by the fusion reactions that power stars. They require the capture of neutrons by heavy atomic nuclei. Building up to progressively heavier elements, there are two main neutron capture processes: the S process, slow neutron capture, which occurs in the interiors of red giant stars, producing elements like barium, strontium, and lead, and the R process, rapid neutron capture, which requires an extraordinarily intense neutron flux available only in extreme environments. The R process was long known to be responsible for roughly half of all the elements heavier than iron, including gold, platinum, uranium, and many others, but its exact site was debated for decades. In 2017, the Gravitational Wave Observatory LIGO detected the merger of two neutron stars, and simultaneous observations by telescopes across the electromagnetic spectrum confirmed that this merger was accompanied by a kilonova, an explosion rich in R process products. The merger produced an estimated 100 to 200 Earth masses of gold alone, definitively identifying neutron star mergers as a primary site of R process nucleosynthesis. Let your body settle completely now. Every atom of gold in the world, and every atom of platinum and uranium, and many other heavy elements, was made in the collision of two dead stars, spinning toward each other over billions of years, emitting gravitational waves as they spiraled closer, and finally colliding in an event so energetic it shook the fabric of space-time enough to be detected on Earth. The universe's most precious metals are forged in its most violent moments. The stellar neighborhood, the collection of stars within a few tens of light years of the Sun, is a diverse and well-studied community. Within 15 light-years of the Sun, there are about 56 known stars, including the Sun. The nearest is Proxima Centauri at 4.24 light-years, a small red dwarf with a mass about 12% that of the Sun. Then come Alpha Centauri A and B at 37 light-years, two Sun-like stars orbiting each other. Barnard star at 5.96 light-years is a red dwarf famous as the star with the highest proper motion observed from Earth, moving across the sky at 10.3 arcseconds per year. At its current distance, it will make its closest approach to the Sun in about 10,000 years, passing within about 3.75 light-years. Sirius at 6 light-years is the brightest star in the night sky as seen from Earth, with an apparent magnitude of about -146. It is so bright partly because it is intrinsically luminous, about 25 times brighter than the Sun, and partly because it is very close. Sirius A is an A-type main sequence star, and orbiting it is Sirius B, a white dwarf of about 1 solar mass compressed into a sphere roughly the size of Earth. Sirius B is the remnant of a star that was once larger and more massive than Sirius A itself, which exhausted its fuel and shed its outer layers billions of years ago, leaving behind the dense white dwarf remnant. The Sirius binary system completes one orbit every about 50 years, and the gravitational influence of Sirius B causes Sirius A to wobble slightly in its proper motion across the sky, a wobble that was predicted and observed decades before Sirius B itself was directly seen. Star clusters are among the most beautiful structures associated with stars. Open clusters are loose associations of hundreds to a few thousand stars, all formed from the same molecular cloud at roughly the same time and sharing similar ages and chemical compositions. They are found primarily in the spiral arms of galaxies, where star formation is ongoing. The Pleiades, the Seven Sisters, visible as a compact cluster in the constellation Taurus, is a well-known open cluster about 440 light-years away, containing several hundred stars with an age of about 100 million years. The stars of the Pleiades are still surrounded by wisps of gas and dust, a reflection nebula created by the cluster's brightest stars, illuminating material from an interstellar cloud the cluster is currently passing through. Globular clusters are far more ancient and densely packed than open clusters. They are roughly spherical aggregations of hundreds of thousands to millions of stars, bound together by their mutual gravity, orbiting in the halos of galaxies. The Milky Way has about 150 known globular clusters. They are among the oldest objects in the universe, typically 10 to 13 billion years old, and their stars are predominantly population 2, old and metal poor, reflecting the era of the early universe in which they formed. The night sky as seen from inside a globular cluster would be extraordinarily different from the night sky we observe from the solar system. The stars in the core of a globular cluster are separated by about 0.1 light-years on average, compared to about 4 to 5 light-years between stars in the solar neighborhood. From inside a globular cluster, the night sky would never be fully dark. Hundreds of stars brighter than Sirius would be visible, and the combined light of the thousands of stars in the core would provide enough illumination to read by, even in the middle of the night on a hypothetical planet. The sky itself would glow with starlight. The collective luminosity of millions of suns packed into a region only a few tens of light years across. Polaris, the North Star, is a particularly interesting example of how individual stars can be far more complex than they appear. From Earth, Polaris appears as a single steady star at the celestial North Pole, about 1 degree away from the actual pole. It has been used for navigation for thousands of years because its position in the sky changes negligibly over human timescales due to its proximity to the pole. But Polaris is actually a triple star system. Polaris A, the brightest component, is an F-type supergiant about 45 times the radius of the Sun. It is also a Cepheid variable, pulsating with a period of about 97 days, though the amplitude of its pulsations has been decreasing over the past century. Polaris AB is a close companion about 18 astronomical units from Polaris A, completing one orbit every about 30 years. Polaris B is a much more distant companion, a F-type main sequence star orbiting the pair at about 2,400 astronomical units, with a period of about 42,000 years. The history of stellar astronomy is also a history of gradually realizing that the universe is far older, far larger, and far more interconnected than any previous generation imagined. The ancient Greeks thought stars were holes in the celestial sphere, or fires on a crystal dome surrounding Earth. Medieval astronomers knew they were lights in the sky, but had no way to estimate their distances. Galileo's telescope in the 17th century revealed that the Milky Way is composed of countless individual stars rather than a luminous cloud. But the distances to even the nearest stars remained unmeasured until 1838, when Friedrich Bessel measured the parallax of 61 Cygni, a nearby binary star system, and found it to be about 10. 4 light years away, the first measurement of a stellar distance using the method of parallax. Today, we measure stellar distances using multiple methods. Parallax, the shift in a star's apparent position against the background of more distant stars as Earth orbits the Sun, works for stars up to a few thousand light years. The Gaia Space Telescope, launched by the European Space Agency in 2013, has measured the parallaxes of about 1.7 billion stars with extraordinary precision, producing the most detailed three-dimensional map of the Milky Way ever assembled. Beyond the range of parallax, astronomers use standard candles, objects of known intrinsic luminosity, including Cepheid variables, RR Lyrae stars, and Type 1a supernovae to measure distances across the Milky Way and to nearby galaxies. Let your breathing be slow and easy now. Let your body be completely still. The stars are above you, every one of them a sun, some of them larger than imagination, some of them tiny and patient and glowing red for trillions of years. The iron in your blood was forged in a massive star that died before the sun formed. The carbon of your cells was made in the helium-burning shell of a red giant. The oxygen you are breathing was made partly in stellar interiors and partly by 2.5 billion years of photosynthesis. You are not just looking at stars. You are made of them. Before we drift fully to sleep, let the stars offer a little more of their extraordinary story. There are things about them that most people never learn, and they are among the most calming facts in all of science. Brown dwarfs occupy the boundary territory between stars and planets, objects too massive to be planets, but too small to sustain stable hydrogen fusion in their cores. The minimum mass required for hydrogen fusion is about 75 to 80 times the mass of Jupiter, or about 8% of the mass of the Sun. Objects below this threshold are brown dwarfs. They can fuse deuterium, a heavy isotope of hydrogen, for a brief period early in their lives, but they cannot sustain the proton-proton chain reaction that powers main sequence stars. After their brief deuterium burning phase, brown dwarfs simply cool, very slowly, over billions of years. Brown dwarfs are genuinely brown, or more accurately a deep reddish brown in visible light, and they emit most of their radiation in the infrared. They were long predicted, theoretically, but proved extremely difficult to detect because of their faintness. The first confirmed brown dwarf, Tade 1, was identified in 1995. Since then, thousands of brown dwarfs have been cataloged, and they are thought to be approximately as numerous as main sequence stars in the galaxy, though their individual faintness makes census-taking difficult. Some brown dwarfs have been found to host weather systems, with clouds of silicate particles and iron droplets circulating through their cool, dense atmospheres, driven by convection in a manner reminiscent of storms on giant planets. The Sun's magnetic activity is one of the most dynamic and consequential of all stellar phenomena for life on Earth. The Sun has a magnetic field generated by the dynamo action of convective flows in its outer layers, where plasma moves upward when hot and downward when cool, in a pattern that interacts with the Sun's rotation to generate complex, large-scale magnetic fields. The Sun's magnetic field is not uniform. It is organized into regions of concentrated flux called active regions, from which solar flares and coronal mass ejections can erupt. Sunspots are dark, cooler patches on the Sun's surface where concentrated magnetic fields suppress the convective transport of heat from below. They appear dark only by contrast with the surrounding hotter photosphere. A sunspot is still radiating at a temperature of about 3,500 to 4,500 Kelvin, which would make it intensely bright if seen in isolation. Sunspots tend to appear in pairs or groups with opposite magnetic polarities. Their number follows an approximately 11-year cycle, the solar cycle, rising from solar minimum when the Sun is relatively quiet to solar maximum when sunspot activity and associated phenomena like flares and coronal mass ejections are most frequent. During solar maximum, the Sun can produce powerful flares and coronal mass ejections that send streams of high-energy particles and magnetize plasma toward Earth. These events can compress Earth's magnetosphere, drive large electric currents in the upper atmosphere, and produce spectacular auroral displays at high latitudes. In extreme cases, such as the Carrington event of 1859, the most powerful geomagnetic storm in recorded history, solar activity can disrupt telegraph lines, set telegraph paper on fire, and in the modern era could potentially damage electrical grid infrastructure and satellites if the event were of comparable magnitude. For planets orbiting red dwarf stars, stellar activity is a far more pressing concern. Red dwarfs, despite their small size and low overall luminosity, are often far more magnetically active than the Sun. They can produce flares much larger relative to their stellar surface than the Sun ever does, and because habitable zone planets orbit very close to a red dwarf, they receive far more ultraviolet and X-ray radiation from these flares than Earth receives from the Sun. Whether life can survive and evolve on a planet orbiting an active red dwarf, protected by a strong magnetic field or adaptive biology, is one of the key open questions in the search for extraterrestrial life. The concept of the habitable zone, sometimes called the Goldilocks zone, is the range of distances from a star at which liquid water could exist on the surface of a rocky planet with a suitable atmosphere. The habitable zone depends strongly on the star's luminosity. Around a bright, hot star, it is farther out. Around a dim, cool red dwarf, it is much closer in. For the Sun, the habitable zone is roughly between 0.95 and 1.7 astronomical units. Earth, at 1 astronomical unit, is comfortably within it. Mars, at 1.52 AU, is near the outer edge. Venus, at 0.72 AU, is inside the inner edge. The habitable zone concept is a useful starting point, but is not the whole story of planetary habitability. Atmospheric composition, planetary mass, geological activity, the presence of a large moon to stabilize the axial tilt, and many other factors influence whether a planet can sustain liquid water and support life. Planets outside the habitable zone can also potentially host liquid water if they have other heat sources, such as tidal heating from a massive planet, a mechanism that may make Jupiter's moon Europa and Saturn's moon Enceladus potentially habitable despite being far outside the Sun's habitable zone. T Tauri stars are young stellar objects, protostars that have become hot enough to be visible in ordinary light, but have not yet settled into stable hydrogen burning. They are named after T Tauri, a young star in the Taurus molecular cloud that serves as the prototype of the class. T Tauri stars are variable in brightness, actively accreting material from their surrounding disks and driving powerful bipolar jets. Their strong stellar winds and ultraviolet radiation are actively shaping and potentially dispersing their protoplanetary disks, even as planets form within those disks. The early solar system, when the Sun was about 1 to 10 million years old, looked much like a T Tauri system, with an active young star surrounded by a disk of gas and dust in which the seeds of the planets were beginning to accumulate. The Sun's journey through the Milky Way is a leisurely but eventful one, orbiting the galactic center at about 230 kilometers per second. The Sun completes one circuit of the galaxy every approximately 225 million years, a period called a galactic year or cosmic year. During one galactic year, the Sun and the entire solar system move through different parts of the Milky Way, encountering different stellar densities, different radiation environments, and potentially different concentrations of molecular clouds. Some researchers have explored whether the Sun's passage through the galactic spiral arms, which it crosses roughly every 100 million years or so, correlates with periods of elevated cosmic ray flux at Earth, or with other changes in the terrestrial environment. The solar system is not stationary in the galaxy. It is a traveler, moving through a slowly changing cosmic environment. The way ancient cultures understood and used stars is one of the deepest connections between human beings and the night sky. Long before telescopes, long before the modern understanding of what stars are, people organized their lives by the stars. The Polynesian navigators of the Pacific sailed thousands of kilometers of open ocean using star paths. Specific stars or sequences of stars that rose and set at the bearings of their destinations, combined with observations of ocean swells, winds, bird behavior, and cloud patterns. The Egyptian pyramid complexes at Giza are oriented with extraordinary precision relative to the positions of stars. The Aboriginal Australians developed complex astronomical knowledge over tens of thousands of years, including observations of the dark nebulae of the Milky Way as constellations in their own right, figures formed not by bright stars, but by the dark, dusty lanes silhouetted against the galactic background. The stellar proper motions, the slow drifting of nearby stars across the sky over centuries and millennia, mean that the night sky as seen by humans today is not identical to the night sky as seen by humans 100,000 years ago, and will not be the same as the night sky seen by humans 100,000 years in the future. The familiar constellations are patterns of stars that happen to lie roughly along the same line of sight from Earth today, but are at very different actual distances. They have no physical association with each other, and as the stars drift in their individual orbits around the galaxy, the patterns gradually change. Orion as we know it will be unrecognizable in about 100,000 years. The Big Dipper will have changed its shape significantly. New constellations will emerge from stars that are currently too scattered to form recognizable patterns. The discovery of stellar parallax in the 19th century, which confirmed that stars are genuinely distant objects rather than nearby fixtures, was the culmination of centuries of observational effort. Copernicus, in proposing the heliocentric model in 1543, predicted that if the Earth were orbiting the Sun, nearby stars should show parallax shifts. Apparent shifts in position against the background of more distant stars as the Earth moved from one side of its orbit to the other. No such shifts were detected for 300 years, not because they did not exist, but because the stars are so far away that the shifts are tiny, less than 1 arcsecond for even the nearest stars. It required the precision telescopes and measurement techniques of the 19th century and the patient determination of astronomers like Bessel to finally detect these tiny shifts and confirm both the heliocentric model and the vast scale of the universe. The Sun will continue to burn for approximately another 5 billion years. In that time, it will slowly brighten by about 10% per billion years. This gradual brightening will eventually cause the Earth's oceans to evaporate and the surface to become uninhabitable, perhaps within 1 to 1.5 billion years, long before the Sun becomes a red giant. The Sun's increasing luminosity is one reason why the window of habitability for Earth may be closing, in geological terms, even though it remains comfortable for the foreseeable human future. In 5 billion years, when the Sun becomes a red giant and ultimately a white dwarf, the white dwarf remnant will continue to exist for billions to trillions of years longer, cooling slowly in the dark. White dwarfs are extraordinarily long-lived objects. They are supported not by ongoing nuclear reactions, but by the quantum mechanical pressure of electrons, which prevents them from collapsing further regardless of temperature. A white dwarf with a mass close to the Sun's mass has roughly the radius of the Earth, packed with about 600,000 times the Earth's mass. Its surface gravity is about 300,000 times that of Earth, and it will cool barely for longer than the current age of the universe, before eventually becoming what we call a black dwarf, a cold, dark, dead stellar remnant. No black dwarf yet exists anywhere in the observable universe. The universe has not been around long enough for any white dwarf to cool to black dwarf temperatures. The oldest white dwarfs we know of have surface temperatures of a few thousand Kelvin, still glowing faintly. In the incomprehensible future, the universe will be populated by vast numbers of these cold, dark remnants of what were once burning stars, the graveyards of the stellar age, drifting silently through the expanding dark. Tonight, the stars are burning, every one of them. Right now, in the constellation Orion, in the shoulder of the giant, Betelgeuse is pulsating slowly, its enormous outer envelope swelling and contracting over months in a slow breath that mirrors the slow breath you are taking right now. In the constellation Canis Major, Sirius A is blazing white and hot, orbited by the cold white dwarf of Sirius B, the ghost of a star that once outshone Sirius itself. In the southern sky, Proxima Centauri is glowing its patient red, flaring occasionally with brief bursts of X-ray light, orbited by its potentially habitable planet Proxima B. And in the Orion molecular cloud, in the dense cold darkness of a collapsing region of gas and dust, a protostar is gathering mass, its core temperature rising toward the threshold of fusion. In perhaps 1,000,000 years, it will ignite. It will become a new star. It will burn for billions of years. It may have planets. Those planets may have oceans. And on one of those planets, in a few billion years, something may evolve that looks up at the sky and wonders what those lights are. The stars are not just scenery. They are the engine of the universe. They are where all the chemistry happens, where all the elements are made, where the raw material of planets and life is forged and distributed. They are old beyond reckoning and patient beyond comprehension, and they made everything, including you. Sleep now. The stars are where they have always been, burning in the dark, in their millions and billions, each one a sun, each one a story. And right now, in this quiet room, in this ordinary body made of extraordinary stardust, everything is still. Good night.